I appreciate that. Okay, reading response questions. Why would amplitude not affect the period? If an object is oscillating at a greater distance from equilibrium, how would it not take more time for a complete period to occur? Well, in general, the amplitude will affect the period. It's just for small amplitudes that the period is roughly independent of the amplitude. So if you have a pendulum and it's swinging, if you call theta equals 0 at the bottom, right? If it's swinging between minus 90 and 90, you're going to find the period is longer than it is when you're just going from minus 30 to 30 degrees, a smaller amplitude swing. Same thing, excuse me, for springs. If you have a spring that sort of has a small amplitude compared to how much the spring can stretch, then the period doesn't depend on the amplitude. But if it gets stretched quite a bit, where you can see the coils of the spring really stretched out, the period will depend on the amplitude. But more generally, why it still doesn't seem to make sense. If it's going a bigger distance here, why doesn't it take longer? Even if it's a small amplitude, why doesn't it take longer to go? And the answer is, well, when it gets, say we take the spring case, when it gets stretched more, there's a bigger force. That bigger force has a bigger distance to accelerate the mass. And so the mass is going much faster when it passes equilibrium, if you've got a large amplitude kind of situation. And because it's going faster, that means it's shooting towards the other side much faster. And you can imagine that that kind of balances out the fact that it has to go a bigger distance, right? Smaller amplitude means it's going slower when it passes equilibrium. Bigger amplitude going faster. At least that makes it somewhat plausible that the effects might cancel out and it could be independent of it, like it is when amplitudes are small. Why do we ignore the mass when we look at the vibrational motion of objects and assume it's mounted horizontally and not vertically? I wasn't really sure about the first part of this. Why do we ignore the mass when we look at vibrational motion of objects? We're certainly not when we're talking about a mass on a spring. The period depends on the mass for the expression that we gave last time. Maybe I'll flash it up there later, but it was 2 pi times the square root of m over k. So the period definitely depends on the mass. We can't ignore the mass at all. Why is it mounted horizontally and not vertically? Well, I guess the short answer is, look, if it's mounted horizontally on a frictionless table, we don't have to think about gravity, so we won't worry about it. Now, I just told you that when it's mounted vertically, there's a simplification that's hard to justify, or it takes a little bit of math to justify. But it's just conceptually simpler when things are oscillating horizontally. Gravity's not doing any work. The normal force isn't doing any work. They're certainly acting as it slides across the table. And we're assuming there's no friction on the table when we draw it that way. You could also attach it to the side of a spaceship in deep space and have it oscillate that way, and then there wouldn't be any gravity to speak of either. Why doesn't the period or frequency of a simple pendulum depend on the mass of the pendulum bob? Well, okay, so this is sort of connecting with the previous one, and I remember why I put this after this to clarify that. The frequency and period of a pendulum doesn't depend on the mass, right? For a mass on a spring, it does depend on the mass. And that's, sort of the same idea as if I drop two objects of different mass, why do they accelerate at the same rate? Seems like one of them's really heavy and one of them's relatively light. Now, it's got to be that air resistance is sort of negligible for both of them. But one could be a really heavy brick, and one could be sort of a light ball. We drop them and they both hit the floor at the same time. They're accelerating at the same rate. It's the same way with a pendulum. It's true that when I pull a mass that's larger to the side, it's feeling a greater gravitational force component pulling it back towards the center, but it also has more inertia, and that inertial effect cancels out the bigger force, right? You might, if you have double the mass, you're comparing a mass m to a mass 2m, pull it to the side the same angle, you're going to get double the force along the direction that it's going to start accelerating, but it has double the mass. And so those two effects on F equals ma cancel out. And we find that the acceleration is actually the same in two cases. Same reason that when you drop two objects of different masses, they accelerate at the same rate. Okay, onward in the chapter. Let's now talk about more generally describing. So again, just like someone was objecting to, here's the mass attached to the spring and going horizontally. So I'm imagining we've got a frictionless table and it's attached to a wall sliding on a frictionless table. I'll call plus x the increasing stretch direction, right? As usual. If I graph the x coordinate of this mass as a function of time, right? Maybe I'm imagining I stretch it to a positive x and then I let it go from rest. You could imagine that the graph would look something like this red line, right? This is x and this is t on the horizontal, right? X starts out maximum positive because I stretched it to the amplitude level, let it go from rest. It zooms past 0, zooms to a negative part. That's where the spring is compressed. Then it goes stretched, then it goes compressed. So it's oscillating like that. And the question I want to address now is, can we get an explicit expression for this function, right? Well, it's not too surprising. It's going to be some kind of cosine or sine. At least it looks like that. For those of you who remember your trigonometry kind of functions, we've certainly touched on those a lot in this course. Well, how do we get it? Well, it really comes from F net equals ma. And I can't remember exactly how Giancoli justifies it, but essentially, this is what we call a differential equation in physics. And you have to use some calculus to solve it. It's not too bad. But you need to know something about taking derivatives of cosines and sines. Many of you know that, but I'm not going to talk through that here. So let's just think about if this mass is, it's oscillating back and forth, and I imagine it's at some random position x. Maybe it's stretched out to a distance x relative to the equilibrium. And x is this direction. Of course, there's a normal force and a weight force, but if I do the sum of the force x components equals max, then normal force and weight force won't come into it. And the only force that's in the net force x component is minus kx, right? If x is positive, then it's going to be a negative force x component, and that's equal to max. And then the question is, how do I find a kind of function where whenever x is positive, ax is negative in exactly this way? And that's part of what is called solving that differential equation. If you've taken calculus before, you may have done applied problems where you write acceleration as the second derivative of position with respect to time. So this is what's called a differential equation. And it's one of the simplest ones because it's got a nice simple cosine and sine kind of solution. Okay, so we're looking for some function x of t, so that if we could compute the corresponding acceleration, the acceleration would be negatively proportional to the position as a function of time. And I'm just going to hand you that. To check that, you need to do a little bit of calculus, and we're not going to talk about where that comes from. So here's the generic form of what x looks like as a function of time. If it's as if I'm picturing up here, right, where it was at the maximum positive value at time t equals 0. In other words, if at t equals 0, it's at x equals a, that means it's at its maximum position and it's at rest. Otherwise, it wouldn't be the amplitude, right? If I released it from a speed at x equals a, we wouldn't be justified in calling it the amplitude. So at t equals 0, I've stretched it and released it from rest. Then x as a function of t is the amplitude times the cosine, right? Cosine usually goes between +1 and -1, right? Maximum height is +1 of a cosine function, minimum height is -1. If I multiply by a, it goes between plus or minus a, and that's exactly what we're expecting, right? This is oscillating between plus a and minus a. And the mysterious part is that, of course, the argument of the cosine is a function of time, but there's this root k over m in there, and we'll sort of see what that means a little bit later. So if I release it from rest at the maximum amplitude, right, stretch it, release it from rest, that's what the function is. Another way I might release it that's not releasing it from rest is imagine that the spring is totally relaxed. It's sitting there with the mass at x equals 0, however I'm measuring that. And I take a hammer and I give it a whack so that just after t equals 0. It's got a velocity, but it's still essentially at x equals 0. So here I'm imagining it's not at the maximum amplitude, but it's at x equals 0, and somehow we give it some initial speed at t equals 0. In that case, it's not a cosine function, but it's a sine function, and the plus or minus out in front depends on which way we give it the whack. If I whack it in the positive direction, then you put the plus out in front. If I whack it in the negative direction, you put a minus sign out in front. Okay, so those are the solutions to F net equals ma. That's where it's coming from. Now, looking at this, we already know the period of a mass on a mass attached to a spring oscillating horizontally, as long as we know the spring constant. But we can actually verify that that's true if you buy that this is the solution to the differential equation. Typically, that's how people would proceed in solving this. They'd say, oh, F equals ma is a differential equation. We solve it. And then I ask the question, hey, looking at that function, what's the period? And here's how you think about the period, right? If I look at the graph here, the period is how long it takes me to get from maximum amplitude to the next time it's at maximum amplitude. How much time is there between the top of the hill and the top of the hill? That's right, from one maximum amplitude to the next time it's at maximum amplitude. So I'm just going to think about it. If I choose the cosine kind of function, that's one where I released it from rest at x equals a. When t equals 0, right, when I plug in t equals 0, the argument of the cosine becomes 0. Cosine of 0 is 1. So this whole cosine is 1, and x equals a. Right, so that's like the top of the hill if we're looking at the graph. And the question we want to ask is, well, when's the next time x is equal to a? And by definition, if we wait till t is equal to exactly what is one period, it should be back at x equals a. Right? That's going to be the first time it gets back to x equals a. That's going to define what one period is, right? If it was at x equals a at 0, we wait one period, it should be back at x equals a. Here's how to think about that in terms of the shape of this function. If I plug in little t equals capital T, the period, well, think about when the cosine reaches its highest point, right? We're talking about the top of the hill on that function I was graphing on the previous page. When is it at its maximum point? In other words, when is the cosine going to be maximum? Well, it certainly was at t equals 0, but also at t equals capital T, the cosine reaches a maximum at t equals 0, when the argument of the cosine is 0, when the argument of the cosine is 2 pi, when it's 4 pi. So the first time it gets back there is when the stuff inside the cosine is 2 pi. And by setting that stuff inside equal to 2 pi and solving that equation for t, you get t equals 2 pi times root m over k. So if you prefer, that's one way to justify where the period that we just wrote down earlier came from. I showed that equation, but I didn't justify where it came from. Here, there's still a little bit of a mystery because you got to wonder, how did you solve that differential equation? But if you ever take differential equations or go on in physics, if you took physics 210, you talk about how to solve that using calculus. Okay, so the period is 2 pi root m over k. Now notice what comes in here is root k over m. So it seems like the reciprocal of the period is more close to what's in here. So let's take the reciprocal of the period. Remember, that's what's called the frequency by definition. Period is how many seconds per cycle. Frequency is how many cycles per second. That's hertz. Here it is. So root k over m, well, 1 over 2 pi times root k over m is f, and that means root k over m is 2 pi f. Okay, so another way to write this equation over here is root k over m is the same thing as 2 pi times the frequency. And so substituting that back into our function up here, I could just rewrite our functions instead of writing them in terms of k and m, the stuff inside the cosines and sines. That root k over m can be replaced by 2 pi f. And that means if somebody hands you this function, you might be able to read off what f is and therefore figure out what the period is. Okay, let's do an example problem. This is on the worksheet that we were using last time. Second problem. Is anybody in the classroom missing one? I think I brought some extras. There's even more people gone today. Lots of people getting their second COVID vaccine, and the MCAT's coming up, and people are sick and you need one, Jaden. There's the track, conference, all sorts of stuff is going on. I just want to do this one together, this problem too. So, and there's not really too much work to do, but we got to read the graph. So I'm repurposing, oops, that's not what I want to hand you. I'm repurposing that same graphic that was on the front of the sheet. And we're told that this graph describes a spring that connects a 1.2 kilogram mass to a wall. We're not told what the spring constant is, but maybe we'll be able to figure that out if we think hard enough. And the spring is compressed a bit, really, or in this case, looks like it was stretched a little bit. And if we take plus x to be the stretch direction, I should really say it's stretched a bit and released from rest, and the mass oscillates on the spring. Suppose this is the function as was given before. This represents the mass's distance from the wall. T is seconds on a stopwatch. Write down a formula for the equation x equals f of t. Okay, now the formula is going to be given by the form that's shown there. And, well, the first clue is that at t equals 0 on here, let me point with my pointer, at t equals 0, the function's at a maximum. So that kind of looks related to the cosine form, right? It's as far as it can get from the wall at time t equals 0. So I'm going to use that cosine form. And what do I need to figure out in there? Well, I need to figure out what the amplitude was, and we already found out the amplitude. I'm not sure if the numbers are the same as the one we did on the previous page, but I need to figure out what the amplitude is. Let's see. It's going between a height of 1/7 and 5/7, so it goes a total distance of 4/7. So it looks like the amplitude is 2/7 for this motion. Right? So I'm gonna leave that up there. You can always pin my video if you want to see me writing on the board, but I'm going to keep that displayed up there while I write on the board. So let's fill in the details here. X equals A. We're going to find out we need a little bit more than this. A times the cosine of 2 pi ft. And we just found out A is equal to, I believe I said 2/7 of a meter, right? So that's what goes in front of the cosine. So it looks like I'd be done if I could figure out what f is, right? That's the only other unknown besides the variable t. There should be a t in there because it's got to be a function of time. How do I figure out f? What was it that we did? This is a good reminder. How do we do this on the front page? Yes, and t we could read off the diagram, right? By using those coordinates. Remember, in the coordinate pairs there, the first one was supposed to be the t in seconds. I didn't put the units on this one, but the 12/13 up there is in seconds, and the 24/13 is in seconds. So it looks like the period is 12/13, right? That's how long it takes in time. Those first coordinates in the coordinate pairs are times. I should have put a seconds on the time axis. It increases by 12/13 in going from the one top of the hill to the next one. So t is 12/13 of a second. Let me just do that down here. And that means that the frequency, so this is how many seconds per cycle, and that means there's 13/12 cycles per second. And remember, that's the very definition of hertz. Okay, so t is 13/12. So I have 2 pi times 13/12 hertz times t. Okay, so that's the function that describes the motion. Questions on 2? I believe I wanted to do 3 together as well. Oh no, I've got a couple more reading response questions. So let's just do these because they had to do with something related to that. Can all simple harmonic motions be modeled using sine and cosine? Tangent oscillates, or at least it's periodic, right? It repeats every pi, but approaches asymptote. So why don't we use that to calculate the period and the frequency? Well, tangent would have a period, but it's going off to infinity, so it would be strange. It certainly doesn't describe simple harmonic motion. You'll find out if you ever take a differential equation class or take physics 210. Simple harmonic motion means a certain kind of motion, and they're all modeled using sine and cosine or combinations thereof. Sometimes they're a linear combination of the two of them, like a constant times the cosine plus a constant times the sine. Can we walk through how the angular velocity is equal to 2 pi f? I didn't talk about the angular velocity, or I haven't mentioned that term in our class, but you see here that we have a 2 pi f appearing. It's a little bit out of focus. There we go. We got a 2 pi f here. Sometimes people call that combination the angular frequency omega, and it's no just coincidence that it's the same single symbol from our angular velocity that we had before. This is called the angular frequency here. The idea is the frequency is in cycles per second. So if I have f, that would be in cycles per second. If I multiply by 2 pi, I can think of that 2 pi as being how many radians there are in a cycle, if a cycle means one complete oscillation. Now, usually you're thinking of circular motion when you're talking in terms of radians, but sometimes when anything's oscillating in any way, people will say in one complete cycle of the motion, let's think of it as if it's going through an angle of 2 pi radians. And they canceled the cycles, and you get units of radians per second. And so we're thinking of, even though something's oscillating back and forth, we can think of it as kind of the same way something's going around in a circle as we did in orbital motion. In any case, I'm going to try not to speak in terms of omega, the angular frequency, just sticking to linear frequency. Okay. Here's the last question. I thought we'd do this together. It's Friday. What the heck? Same kind of things. We need to look at those equations. And in fact, I've got I left something off of the previous problem. I realized I forgot something, and that is, this is not the answer. Can anybody see why this isn't the answer? This can't possibly be the function that's drawn up there. I'm pointing to my 2/7 m cosine of all that stuff times t. What is this oscillating above and below as time goes on? What's the middle line supposed to be?
0.
Yeah, it's 0, right? Because the cosine's going between -1 and 1, and that means this whole function's going between plus 2/7 and minus 2/7 meters. And that means its average line should be 0. Now, if you look at this function here, it's not oscillating around 0. It's oscillating about, well, let's see, the lowest y coordinate there is 1/7, the highest is 5/7. So it looks like the middle line, which I didn't draw very well, it doesn't look like it's in the middle, but it's at a height of 3/7 of a meter. So it's oscillating about 3/7 of a meter, going up 2/7 of a meter above that and below it. So to be technically correct on this particular problem, I've got to add 3/7 of a meter onto it. And that would give me my x as a function of time. And that's because, look, on average, it's going to sit at 3/7. It'll go a little bit above that due to the cosine. It'll go a little bit below that when the cosine's negative, but it's going to be oscillating around there. How much will it go above it? Well, it'll go above it by 2/7, right? That'll make it to a height of 5/7, and that was the maximum point it had on there. I didn't purposefully put that in there. It just that happened to be how the graphic was, so it made it look a little bit more complicated. Okay, let's go in the reverse direction. Here, instead of being asked to give the equation, you're actually given the equation for the motion, okay? And we're asked a bunch of questions about it. So we're told that these numbers, the 0.650 and the 8.40 that are appearing in that equation, have appropriate SI units, but I didn't put them in for you. And so the first question is, what are the SI units for the numbers 0.65 and 8.40 that appear in there? Who wants to volunteer one?
0.65 would be in meters.
Right. How about the 8.40?
Would be like hertz per second.
Yeah, I mean, it seems like it's going to be in hertz, although, as we said in what I was writing on the board earlier, when people write this 2 pi right here, they think of it as having units of radians per cycle, and the cycles cancels the cycles in the hertz. So 2 pi f would have units of radians per second, or sometimes people say, as I know it's confusing, but radians are no units at all. In other words, the definition of a radian was a ratio of two distances. So a radian is just the same thing as no units at all. So people would tend to say that number that appears in front of the t has units of 1/seconds, but no one would fault you if you said radians per second. Let's see another way that makes sense. It makes sense because whenever you have a trig function, or in general, any kind of non-trivial function like cosine, sine, tangent, exponential functions, the argument of those functions have to be pure numbers. In other words, the things that you're putting into a cosine or a sine or a tangent or exponential or logarithm should be something that has no dimensions, no units. Now, if I'm putting in t in seconds, then the thing that's in front of it better have units of 1/seconds, so that combined together, they have no units whatsoever. So another way to think of the 8.40 as having units of 1/seconds to cancel out the units of the t there. I don't know, seems a little bit tricky for Friday anyway. What's the amplitude? Most of these, I think we can just read them off. 0.65 meters, because we were told it's in SI units, right? What's the frequency of the oscillations? How do I look at that and get the frequency? Yeah, 8.4, 1/seconds is 2 pi, that's equal to 2 pi f, and I solve for f, right? It's not an interesting number, but the frequency you get is 1.34 hertz in that case. If you set 8.4 equal to 2 pi f and solve for f, you get whatever number I just said. What's the total energy stored in this oscillator? In other words, we talked about earlier that as it oscillates, you get points where there's a lot of potential energy and other points where there's a lot of kinetic energy, but the total energy is staying the same. What is that total energy in joules here? How would I calculate that?
Would you find V max and then use like use like a 1/2 mv squared? Maybe?
I sure could do that, although I will say that's the difficult way to do it. There's sort of a one step where I can just calculate something based on, I don't have to calculate a Vmax and then calculate 1/2 mv squared. How can I use the 0.65 meter amplitude to more directly calculate how much energy is stored in it? Like Nafis is thinking, oh, as it's passing the middle, it's going with its V max. And so there's no potential energy at that point. We'll just calculate the kinetic energy and we'll be done. Well, the problem is I've got to figure out what V max is. That's not a problem. We gave a formula for it. You could do it with energy conservation. But how could I use the amplitude to get it more simply?
One half Ka squared.
1/2 Ka squared. That's right, because the potential energy stored in a spring is 1/2 Kx squared. And the total energy is kinetic plus potential, but when it's at the maximum amplitude, right? When x equals a, 1/2 Kx squared. When I plug in x equals a, and we can just read that off as 0.65 meters, I think it was, right? Then I guess I'd be done, although maybe it's not as quick as I was thinking we could do it because we don't know what K is, huh? We don't know what K is yet. So maybe Nafis's suggestion isn't any more difficult than what I was going to suggest. Okay, so that's one possibility. We use that formula for Vmax that we got earlier on. Figure out Vmax and do 1/2 mv squared. We were given m. Let me just ask it a different way since I've got this up here. How could I find K? Right, I could use that relationship between either T or F, and the root K over M is related to F, or root M over K was related to T. We already figured out T, so we could figure out what K is from that. And I actually think that's no more easy than what Nafis was suggesting. So either one of those, right? Go to a point where it's either all kinetic energy or all potential energy. And you might think about both of them and see if one of them is easier. In this case, it doesn't really seem like it. Yes?
Is the 1/2 Ka squared only applicable if it's cosine function?
No, it applies if it's a sine function too. Did you say how?
Yeah, because if we use the x equals plus or minus a sine, that's if x equals 0, t equals 0.
Right, but at some later, that's where, so the question is, can I use the sine or the cosine function? Is this kind of technique applicable to both of them? So let me just draw some pictures. If I stretch it to its maximum position at time t equals 0, right? So I'm stretching it up to what's going to be the amplitude once it starts oscillating, right? I stretch it, release it from rest, then it's going to be that cosine kind of shape, right? What about if I compress it to its minimum position, right? I push it in a little bit and release it from rest. Well, then instead of being at a positive, this is the x-axis, instead of being at a positive x at time t equals 0, it would be down at a negative x at time t equals 0. Here's negative a. So it would look like a negative of a cosine function there. It would go like that as time goes on. Whereas the sine was coming in, if I said, well, let's leave it at time t equals 0, it's just at its equilibrium position, but we give it an initial velocity by hitting the block with a hammer. And then just, a microsecond after t equals 0, if I hit it in the positive x direction, it starts heading towards positive, and then goes down like this, and so on. That's going to be a sine kind of function, right? Sine is at 0 when the argument is 0, and it starts heading upwards towards its first peak. If I hit it in the negative direction, it's going to start heading down like this and doing that. Now notice that in each of these 4 cases, it's oscillating between the same kinds of amplitudes. If I know the amplitude, there's always going to be some time where it's at its maximum position. Those times are going to be different depending on which one I choose, right? But there's going to be some time when it's at its maximum position, and then there's going to be no kinetic energy in there. And the potential energy will be 1/2 kx squared with x equal to a at that time. So it doesn't matter which one I choose, there's always going to be some times when it's at that. More generally, you might have, I've got too many things drawn in black here, but you might have a situation where none of these happen. Maybe I released it from rest at a time just before t equals 0, and it starts heading down like that. That would be neither a cosine nor a sine kind of function, but it turns out it can be a number times a cosine plus a number times a sine can be written that way. We're just not going to deal with those in this class because they're just more confusing. In any case, in all of those cases, there's going to be some time when it's all potential energy, and that by definition, x will be a at that point, right? Because that's what the amplitude means. It means where are you at when it's all stored in potential and there's no kinetic left? Okay. Was there one more question on here? Find the kinetic and spring potential energy when the mass is at position x equals 0.36, where x equals 0 is the relaxed spring position. Well, this requires just a little more work because it's neither, kinetic energy doesn't involve V max. It's going to have some, so it's some random position, right? Which is less than the maximum amplitude, right? That x that's given is not at x equals 0, but is not all the way to the outside either. So what are we told here? Well, we're told well, let's write down the equation, and then I'll unshare my screen. X equals 0.65 times the cosine of 8.4 t. We might need some of the work that we've done so far. And let's calculate what the kinetic energy is and the potential energy is. Probably the easiest one to do is the potential energy, right? The potential energy is 1/2 kx squared, and we've got to have calculated the k. We're going to get the k from the period, right? We would say, I looked at this, saw the frequency. From that, we can calculate the period, and if I know the period, we knew the period is 2 pi times root m over k. If I know the period and I know the mass that was given, we can solve for k. Oh, there's a little bit of work to be done there, but everybody can probably imagine how to get that k. And now we're given an x, so we can figure out what the potential energy is there. Everybody okay with that? Then to get the kinetic energy, well, I could use some, energy methods that we've done before, but there's an easier way to do this, and that is that the total mechanical energy, which we've already calculated in the part right before, the total energy, we call that mechanical energy, that's the sum of kinetic plus potential, is equal to kinetic energy plus potential energy. If I've got the potential energy, and we've already calculated the mechanical energy above, I can get the kinetic energy from the total mechanical energy minus the potential energy. So I get, they're not interesting numbers, but the potential energy is 1.11 joules. And then when I do this subtraction using part D above, the kinetic energy is 16.0 joules. So it's going pretty fast there relative to how much energy is stored in potential. And that's all I wanted to talk about with chapter 11. And it looks like it's close enough to the end that I'm not going to start chapter 10. So that worked out perfectly. So as I mentioned, there's a homework assignment on chapter 11. There's a small number of problems. I really tried to cut it down to just bare bones, nothing too confusing that I could see on there. I'm going to make that, I don't know that I've set the due date for it, but I want it to be due, I think, our exams, I'll make it due on Monday at midnight. So you try it this weekend. There's just a small handful of problems. We can address any questions you have on it on Monday. And as usual, if you have other questions, bring them to class on Monday and we can spend a good amount of the time talking about that. I may want to start the fluids material But my first priority is to make sure that you're comfortable for Wednesday as much as possible. Other questions or concerns? All right, have a wonderful, oh, yes.
Could you show part D one more time? Could you like show what part D asked real quick? If you would like share your,
Yes, sorry. The question is, what's the total essentially mechanical energy stored in the oscillator? That is what, where you suggested, I'm assuming that's Nafiz talking, I couldn't really tell. That was where you suggested finding Vmax and using 1/2 mv squared. And I said,
Yeah.
well, you could also figure out what K is and use 1/2 Ka squared.
okay,
But either one of those is the total energy. And then I'm using that in my part E solution.
got it.
Oscillations are going to be on the exam. Think of it as light coverage, especially because it's the last part. There might be one small problem on it, so it's not going to be the major focus of the exam.
Do you have the values for like K and those last two?
I do, and that's one of the things I'll try to post, but if you want to have them, I'll write them up here right now. So A and, F, I'll write down B. F was 1.08 hertz. That was B. C, K was 55.6 newtons per meter. D, let's see, what is the Mac? Oh, I'm sorry. I'm looking at the front page. Yeah, I'm looking at the front page. That's, geez. I had already clipped it together the wrong way. Okay. We can read off the amplitude. We can read off the frequency is 1.34 hertz. That's part C. Part D was, the total energy was 17.14 joules. E, mechanical. Sum of potential plus kinetic is 17.14 joules. And then E, I got calculating the potential energy just from 1/2 kx squared was 1.11 joules. And then I subtracted that from the total mechanical energy to get the kinetic energy of 16.0 joules. I obviously rounded a little bit there, but yeah. Okay, if you don't have questions, have a great weekend. Otherwise, hang out for a minute and we can talk about whatever you need.